All right, so good afternoon, everybody. Welcome back to DSP. And today we will continue to look at lecture 3, and then we have a new one, lecture 4. So in case you haven't downloaded lecture 4 materials, please do it from EE class. But otherwise, we will start from where we were last week. So lecture 3 is about quantization. That's the key word. And quantization leads to quantization noise. Okay, so we will just take a look. All right, so just recall last time we mentioned just to be reminded that C to D conversion, where D stands for discrete time. From continuous time to discrete time, there is a conversion, and the mathematical expression is such like that. Here we have a continuous time signal right there, and when we look at it, when we measure the value at integer multiples of the sampling period, n are integers, then we have a sequence of numbers. X and the discrete time signal basically is a sequence of numbers. But last time we mentioned that we, strictly speaking, 严格来说, strictly speaking, we do not call x of n digital yet. We cannot yet call x of n a digital signal. The reason is because when we say digital, that means all the numbers need to be represented using binary codes, zeros and ones, right? So x of n are real numbers with infinite precision, and they cannot be called digital yet. So therefore, we need to make it digital before applying any computation, right? So how do we do that? So kind of block diagram right here is that after we get the sequence of numbers, real numbers, we will need to quantize the number first, introducing quantization levels. And then, so the basic idea really is rounding to the nearest quantization level. Basically, in Chinese, 45 rule. It's very, very simple. So after we define the quantization levels, then we can just quantize, just approximate our signal to the nearest quantization level. And the result is denoted as x hat, Mao Zi hat. And after that, could be quite straightforward that then we need a coder. We need a coder to turn this quantization levels into binary codes. And the resulting, so it's a convention, the 习惯上 convention that we will just assume that we define the full scale to be plus or minus xm. That's our full scale. So that after quantization, our signal becomes clipped. It's limited within plus or minus xm, limited within the full scale. And then after that, our convention goes that after coding, then let's say the result is in between plus or minus 1. Okay, it's normalized. So the results are normalized. Right, so that's kind of the overall idea. So in the next page, let's look at the quantization levels. So in this example, let's see. So this is, right. So it's rather easy. So here we are looking at a kind of stair-like function. So basically, this is a result of finding the nearest quantization level, right? So and kind of terminology right here, delta. Here we have integer multiple of delta, 1 delta, 2 delta, 3 delta on the positive side. On the negative side, we have 0, of course. That's also one level. 0 is a possible level. 0 minus 1 delta, minus 2 delta, minus 3 delta, minus 4 deltas. So in total, how many steps do we have? In total, we have 8 steps using 3 bits. And it makes perfect sense because 2 to the third power is 8. We have a total of 8 levels. From minus 4 to plus 3 of delta. So let's do a simple calculation. Let's be clear that now we have, if the full scale is plus or minus xn, then delta has a very simple definition. We define delta to be what? To be 2xm divided by 2 to the third power, where 3 is the number of bits. number of bits. Okay, that we're going to be using in our code. Okay, that's straightforward. Okay. Now, of course, later we change the number of bits, 8, 16, 24, something like that. Okay, to represent each number. How many bits do we want? All right. So let's also again mention 2's complement. So in 2's complement representation, of course, 0 is represented by 0, 0, 0, the binary 0, for sure. 1 is represented by the binary 1, 2 is represented by 2, 3 is represented by 3. That's pretty straightforward. But be reminded that for the most negative number, we would encode it by 1, 0, 0. So now the benefit, the advantage of this is the advantage is now the first bit becomes the sign bit. The first bit. Now 1, 0, 0, or 1 whatever. This becomes the sign bit because it tells that whether or not this number is negative. 1 being negative, 0 being positive. That's a convention. This is the protocol, and then above that, 1 level above that now becomes 1, 0, 1. Right? 2 level before that becomes 1, 1, 0, and so on. So you can imagine this is pretty systematic. 是很有系统性的. It's pretty systematic so that we can have an arbitrary number of bits. When we increase this number of bits, you also know how to encode quantization levels into binary strings. 二元的字串的 binary strings. Right? So far so good. So in the next slide, let's do so last time we had the exercise, right? We have this exercise. Now, suppose that the full scale is plus or minus 1.6 volts. If that's a full scale, and we have how many bits? We have an 8-bit representation of different quantization levels, right? So the first thing, let's figure this out. Exercise. Now, if full scale is, if xm is 1.6 volts, which has a physical unit, that's okay. And now, let's first figure out then what's delta, right? We need to first find out what's the quantization step. What's the quantization step? So now delta, of course, according to this expression, delta becomes 2 times xm divided by 2 to the how many bits? We have 8 bits, right? So divide that. Let's try to figure this out. 2xm, just simple calculation, 3.2 volts. Divided by 2 to the 8th power, that's 256, right? Is that right? Yeah, 2 to the 8th number power. So the quantization level is, you tell me, the quantization level is, looks like 1 over 80. Yeah, 80分之一, is that right? 1 over 80, yeah. 1/80th volt, or, if you will, 0.0125. Seems like that's the answer, volt. That's the quantization level, quantization step size. I should say quantization step size. Step size, 一步一步往上跨一步有这么大跨距. Step size, 1 step up. If you go 1 step up, that's the level. Right, so far, so now we are ready to figure out then what does this string represent? This is a binary string of 8 bits, right? What does it represent? And first of all, the first bit is sign bit, right? So sign bit, so we know that then to calculate. So now x, finally x after quantization, let's say x after quantization would be negative something, right? Negative, so I recommend, now it's negative, now we know that the rest is going to be adding up, going up, right? So it's going from the most negative possible value. It is going to go from there and go up, right? Depending on what's the number right here. So we look at the number right here, the rest is so many times delta. How many times? 1007 bits representation remaining. Or if I recollect, let me try to remember. The first is called a sign bit. The next is called what? Is it called mantissa or something? It has a name. The rest. Does anybody remember in computer architecture or whatever? Is it called mantissa? Does that ring the bell? 有勾起你的回忆吗? Does that ring the bell? Mantissa? Anyway, that's the whatever. Don't worry. Anyway, so we are going to calculate this because it's going to, we already know that the first is a sign bit. So it will go from the very bottom and counting up, right? We need to go from the very bottom to go up. Go from the very bottom to go up, and then the rest of the string tells us how much of the quantization steps do we go up, right? How many steps do we go up? Yeah. So this how many steps do we go up? So we need to convert this to decimal. 把它改成十进位. It's easier to think in decimal, right? Nothing wrong about that. So can anybody tell me what's the decimal of this? 100 sorry, in Chinese. 100101. What's the decimal? Can anybody tell me? 这是多少? What's the decimal? 十进位是多少? 70 73 谢谢 73 what a lousy number. It's a prime number. I didn't realize. All right, so now minus 1 xm is minus 1.6, right? Plus 73 steps up. And one step up is 1/80th. So I'll leave you to figure out what then is this number. And the final answer is how many? Yeah. 73哈. So yeah. So the rest become pretty tedious. Okay, so 到剩下很琐碎了哈. So any question here? Does everything look correct so far? Does it look correct? Does it agree with your answer? Now this is my answer, my way of solving it. Okay. And remember, now the result is still in a voltage. The result is still has the unit of volt or whatever other unit, okay, amp or something. Yeah. Okay, so that's how this binary string represent, given the full scale. And suppose that I should state that, I should have said that we are using the two's complement code. So if we use the if we all agree to use two's complement, then this answer is that. Then we have an answer we can calculate. Going from the very bottom and count how many steps up do we go up using two's complement. Okay, so far so good. So far so good. 有对吗? 对点个头嘛. Is it correct? I need to be reassured. Okay. I forgot. Is it Jane Austen or a British writer? Jane Austen还是哪个 British writer? In one of her books, I remember she said that when two young people fall in love, they need to constantly reassure their love. 要常常再确认啊。真奥斯汀 reassurance. Yeah. I need to reassure my answer. I'm not entirely sure if you love this answer or not. Right? Okay, so that's that. So now comes something that I really want to communicate to you. Okay, this is important concept, very important concept. So let's say we have an additive noise model for the quantizer. So of course, this if you take a look, x-axis, y-axis, so quantization is a function of the input, right? Given any input, any real value input, you find the nearest integer by rounding to the nearest quantization level. That's a function q of x. Yeah, of course, that's correct. Input being the sample, discrete time samples, output being quantized. Yeah. X hat is a function of Q of X. Yeah. So far, so good. But in practice, you are encouraged, we recommend you, the textbook recommends us to think of it in an alternative, with an alternative interpretation. Okay? This is 比较另类的 alternative, 这是比较另外的 alternative interpretation goes this way. Still, we have the input. And please force yourself to think of the output as if it's an input add an error term, right? Output is input plus error, because it's an approximation. Quantization rounding is approximation. Therefore, it introduces an error. So that's really the idea. Quantization introduces an error. And here is just that we denote the error by the letter E, okay? 就是用 E 来代表 error, E represents error. So now output is input plus error. So that's a common way of thinking when you have any sort of approximation. Think of this way. Think of it this way. Yeah, that's a recommendation. Okay? Can we agree on that? We'll get used to this. Okay? Try to think of quantization as if it introduces a noise. Because it's an approximation, so there's noise, there's an error. Yeah, so that's the context to summarize. We approximate X as if it's the original input plus a noise term, E of N. That's a concept already, just by redefining, shifting the terms around. So basically we are saying, basically we're also just equivalently, you can write now error is the output minus the input. Okay. All right. So with that, we can develop this concept further. You may wonder, 你可能会想为什么? You may wonder why do we call, sometimes we interchangeably, we call the error a noise. Error and noise, okay, yeah. So you may wonder why do we, in what sense do we call, why do we call, sometimes I call this error term a noise term. Noise, why? So now we can just start by looking at this example, okay? Looking at an example first, yeah. Suppose that now we have a discrete sequence that goes by 0.99 cosine n divided by 10, okay? Cosine n divided by 10. And so you see that this waveform, your input signal is periodic. Yeah, it looks periodic. It's cosine. Yeah, just cosine, right? Yeah, it looks periodic. And then, so suppose that this is the original input signal, and now we quantize it with 3 bits. The result of quantizing with 3 bits, so as we mentioned before earlier, we have 8 levels, right? Start from here, most negative level, 1, 2, 3, 4, 5, 6, 7, 8. 8 different levels. 8 different levels, and you can just, this makes a lot of sense after quantization. After rounding these continuous values, we end up with a signal like that. The signal end up, all the samples can only occur at one of the 8 levels. No other choices after quantization because of rounding to the nearest level. So far, so good? Yeah. So now, using that definition, right? So if we subtract which from which? If we subtract, no, we add this to that. No. If we subtract this away from that, so the difference, basically, the difference becomes, we can calculate the difference between the 2 signals, and that's what we define as the error, right? Calculating the difference. That's what we're going to do in the next slide, okay? So we'll take a look at the difference. Now, so we can take a look at the difference. Taking a look at the difference, and that's just the same as B part, okay? So continuing from the previous page, that's the result after quantization, the output of the quantizer. The output of the quantizer, and now the difference. Now that's the error we're talking about. That's the error introduced by quantization. Now the calculated difference, okay? So you look at this, that's the error as defined previously. And we recommend you to think of it as this way, as if the quantization introduces an approximation error, and the error signal look like that, using 3 bits. So C is quantization using 3 bits. But now what is D? D is also quantization, but using 8-bit. Using 8-bit, now we increase the resolution. 解析度提高啊. We increase the resolution and see what's going on. So when you take a look at D and C, so here I'm asking your opinion, okay? If we take a look, comparing C and D, which one do you think looks more random? This is an open-ended question. Which one do you think is more random? D is more random. Why? It's just more random. Why? Yeah, the things can go deep. Yeah. Why? Anybody? Why do you think D is more random than C? What do you mean more random? What's your definition of random? I randomly selected this course. 哎，真的有吗？乱说。One moment you were randomly selected. The first 第一阶段选课 you're all randomly selected. You're randomly born into a family. Anybody? Do you feel like you're randomly born into a family or a country? 先前有个网络的 app 有没有？那个投胎的那个，就 that will assign you your next life to a random country. It's really hard to get born in Taiwan. Do you know what I'm talking about? 网络投胎 APP. So what do you mean random? See, no. How many of you feel like D is more random than C? D is more random than C. Okay, most of people, any opinion? Why? Yang Jiamin, why do you think? Okay, so let me translate. So now you mean that in C, this part looks not random, right? This is really doesn't look random, right? Yeah, that's the point. Anybody else? Yeah, anybody else? Then how do we define randomness? Anybody? Yeah, 你说 yeah, 燕如 yeah. Oh, how do you mean couple? It's more correlated. It's more correlated. Yeah, you still see this part, right? It's certainly correlated with the original signal. Whereas D now, with an increase in the resolution, now we have 8 bits. Indeed, the error becomes more random. Right? So when error becomes more random and you play it as an audio signal, it sounds like noise. Let me say that again. When you have a kind of random-looking signal visually, if you listen to them, they sound like noise. Okay, so that's one reason maybe why we call the quantization approximation error a noise term. Okay, so thank you for your opinions. Yeah, so I think these things can go deep from here. That's what I want to mention. So now let's take it slowly. What do we mean random? Now, this is a situation of having 8 bits versus 16 bits. Okay, 8 versus 16. So in 16-bit quantization, and I believe it's still using that signal, using that cosine signal. Okay. So if you just calculate the statistics, you can find out, you can start to plot the distribution of the quantization noise, quantization error term using histogram. 这个长条图, using histogram. Whatever terminology, histogram. Using histogram, yeah, okay. And we know that the quantization error is going to be bounded in between half of the step size, right? Yeah. So the largest error you can get is half the step size, by the way. Delta divided by 2. That's the maximum error you can get. So now, of course, we know that the quantization error is bounded in between plus or minus delta divided by 2, okay? Yeah, plus or minus delta divided by 2. So that's for observation. But if you take a look, now, which one is more random? I argue that this is more random than that. Because uniform, this looks more uniform, more of a uniform distribution. And we know that uniform distribution is the most random possible distribution if your random variable is bounded in between an interval. Let me say that again. Yeah. 我用中文讲一遍好了。最 random, you can argue 最 random the random variable. The most random variable is uniform distribution. The theoretical foundation, I use English. The most random variable is uniform distributed. Okay, yeah. And if you're interested in the theoretical foundation, is information theory, the highest entropy. Yeah. So anyway, so in that regard, so this is more of a uniform distribution. Whereas here, the distribution is almost uniform, except right here, it's kind of not flat, right? Not entirely, not as uniform as using 16 bits. Okay, so this gives you a kind of an observation we can make right here. The more bits we have, the more uniform the quantization error becomes. Okay? If you have increased the number of bits, we increase the uniformity in the quantization error as a random variable. Okay? As a random variable. Yeah. And here's also a small exercise from here. You ask yourself, then what's the full scale right here? Maybe let's yeah, 我们可以来试试看啊。Then here, a small exercise before we move on. What's the full scale? What's the full scale when we have this 8-bit quantization right here? Okay. Think about it for 1 minute, right? What's the full scale? If the quantization error, if I give you this plot and ask what's the full scale? What's the full scale? 1 minute. Okay, so it should be, so let me try to see if I can figure this out, okay? What's the full scale? Now, we are given this plot, and immediately we can tell what's the quantization step size, right? Error is bounded in between plus or minus that. So we know that here, as I said, delta divided by 2 is this largest possible quantization error. That's half of the step size. 一半嘛, half of step size is the largest possible error. So that gives us about 4, approximately. Yeah, I said approximately. That's the half of step size, right? And how many bits do we have? We have 8 bits, right? So we now know that 2xm is 2 to the 8th bit times the quantization step size. Yeah. That's 2 to the 8th power times 2 times the half, right? So we can move on, and approximately, I don't know exactly, okay, this is not exact, but approximately. No, I mean, this is approximately, but this, yeah, approximation goes right here, yeah. So from here, we have how many, yeah, this is 256 times a times 10 to the minus 3rd power, is that right? So we have roughly 2048 times 10 to the minus 3rd. So that gives us how much? 2.048 volt. Maybe volt, maybe not. It doesn't give us a number. Let me just refrain from using a unit. Refrain. Yeah. So that's how you figure out approximately what's the full scale 2xn is that, so therefore xn is probably 1 point. Yeah, it's probably 1.0. Let me just stop right here, okay? Kind of to double check. So from here, you can tell the full scale is 1.0. Okay, so yeah, so kind of the one nice observation, we can form a hypothesis. When we increase the resolution, when we increase the number of bits we use, now the error would generally become more and more uniform, more and more uniformly distributed. Is that making sense? Yeah, it's making sense, right? Yeah. Okay, so now given that we are ready to talk about a noise model, right? Now, as I said, now you can further think of your quantization noise as a random variable because they look uniformly distributed. Okay, so let's I suggest now we recommend that we can think of the approximation error as if it follows a uniform distribution in between half plus or minus delta divided by 2 as a random. So now here P is the probability density function. Probability density function. Right here, P is, do I write it? Did I write it right here? Yeah, so let's read this first, okay? And this is a figure from the textbook, by the way. So if we assume that full range is plus or minus that, and we have so many bits, somehow in the textbook it recommends that B equal, number of bits is B plus 1. It's very kind of a strange setting. But anyway, so the important point, this is still true. This is always true. Now the quantization noise can be approximated by a uniformly distributed random variable within this interval. Okay, within this interval, that's still correct. Plus or minus half of the step. Yeah, that's obviously correct. Yeah. All right. So there are a few, there's one advanced question now we can ask right here. Remember now the notation. Let me read the notation first. Okay. Now we have P of E being a random variable. Okay. Now P is the probability density function in the sense that when we take the integral of P, the result should be 1. Okay. Probability density function. So let me make a few notes before we move on to talk about to answer that advanced question. Okay. So now there are a few observations that we can make. Yeah. No observation. I mean, there is a few things that we need to reassure with you. First of all, is that now P is sometimes say E of n. E of n follows this probability density function. P E of n of E. And this is the 几率密度函数 probability density function. So just please, if you have learned this, probability in that any density function needs to be normalized. So that is integral P within the range, within its range. Should be 1. The area under the probability density function, that area needs to be normalized. Yeah? So if you take a look, indeed, that's the interval, and the probability density is a constant of 1 over delta. Okay? Now, that's a density function. But now from here, as a random variable, now you can further develop and ask a few questions. What's the expected value, right? What's the expected value? What's the variance, and so on and so forth? What's the entropy? Such kind of concepts can be developed. Okay, so now let's use the power as an example. Okay, so basically we are asking you. Obviously, the expected value is 0. Okay, expected value is 0. So now the variance, power. when we say power of a zero mean random variable, that means we are talking about the variance. Variant of this random variable. Variant of En, okay? As a random variable. Now En is a random variable, okay? Variant of En, that's the power, okay? And as a following this definition, what's the definition of variance? The definition of variance is an expected value, okay? It's an expected value of E minus the mean square. That's the definition of variance, right? And what's the mean? Mean is 0, okay? Mean, and we know that now this is a zero mean random variable. Zero mean, the mean is 0. And then how do we calculate this? Then given any density function, right, we can calculate the variance by an integral, okay? Now we need to take this expression En square and P and weight it by the probability density function of E and integrate it over the range, over possible range. This is getting, the notation is not the best. But anyway, so still take the integral. That's the idea. Okay? Take the integral of this. Treating E of n as a random variable. So we are going to evaluate this integral of E squared. Actually, E minus mean square. Okay? That's a variance. Variance, and it takes a weighted 就有加权重嘛 probability density function and do this integral. Okay? Do this integral, the notation is really 太多字 So let's change the variable. Let's define U equals En. Yeah, that's a good choice. Let's just rename everything by U. By U. Okay? Then U square, then P-En. Now what's this? This is a uniform distribution, right? So this part is pretty easy. The density, what's the density? Density is a constant in this case, right? The probability density function in this case, because it's uniform, so we have 1 over delta right here, okay? 1 over delta right here, a constant, U square, constant du. So this is a rather simple integral. We'll integrate from minus to plus, and then U square times constant 1 over delta du, right? So that's pretty straightforward. That becomes getting straightforward, right? We all know how to do the integral of U square with respect to U. 积分 U 平方 it's pretty straightforward. So we know after some calculation. So I'll leave the details. But if I remember correctly, I think that the end answer, you can verify the power, which is the variance of this random variable, is going to be this, okay? Very useful expression. Delta square divided by a factor of 12. Power of the approximation error, the variance of your approximation error, which sounds like or look like a noise, the power is delta square. It's proportional to delta square with a factor of 12 at the bottom. Okay? So such kind of thing, really we can seriously think of your quantization error as if it's a random variable. Maybe that's the point I want to deliver. Seriously, we can think of the quantization error as a random variable. Seriously. Question here? Any question? Is it something not clear here? 我觉得需要 more discussion. Is there anything you want to pay more attention to? 有什么想要再了解更多的地方？ Yeah? Okay, so now, so a few comments I want to make right here on this slide. So in here, we see a plot which assumes that the quantization error is uniformly distributed. Okay, that's an assumption. That's a pretty good approximation if your solution is high enough. Yeah. But there are a few extra assumptions that people often make. Yeah, some additional, some extra assumptions that people in this field often make. Yeah, so let's go through them. Assumption number one, additional assumption number one, we often assume that the error is stationary. Error is stationary. That is to say, now n can go from 1, 2, 3, 4, 5. Yeah. Now we have a sequence of random variable or random process, if you will. Now, if every error is a random variable, now we have a sequence of random variables. When we say stationary, that means that the distribution stays the same. The distribution is the same for every sample. It's not like at first you have a smaller power, and when time goes further, suddenly the power increases. It's not like that. Okay, the distribution remains stationary. It's always the same distribution for all n. Okay, that's what we mean stationary, 静止的稳定的静止好像 stationary A bit of glossary, stationary. Some people translate it as 静 Maybe I shouldn't say 止, but 静 stays the same. The distribution stays the same. A second assumption, error is uncorrelated with the signal. Now think about this. If you just approximate any real number by the nearest integer, and the approximation error, 如果我们去45任何一个整数, if we approximate any real number by its nearest integer, 45 right? What's the quantization error right here? The quantization error is in between plus or minus 0.5, right? Rounding, yeah. And then here we assume that error is uncorrelated with signal. Does that make sense? That makes sense. Uncorrelated. So it's like asking your height, right? Your 身高 in centimeters. 1 meter 73, 173 point something centimeter. That point something, is it uncorrelated with my height? With everybody's height, right? It's not like the taller you have, the taller you are, the larger the quantization error. There's no such relation, right? That's what we mean correlation. Is your quantization error is a fractional part, 小数部分 uncorrelated with the integer part. 小数部分跟整数部分有没有 uncorrelated? Okay, that's the question we are asking. Yeah. So often people in this field, in the field of signal processing, assume conveniently that error is uncorrelated with the signal, and it makes a lot of sense. Yeah. The error can be plus or minus, but is uncorrelated with the input signal. Think about this, okay? Uncorrelation. There's no positive or negative correlation. The correlation, or should I say the correlation coefficient is 0. Yeah, that's what we mean. If you treat the input as another random variable, and the output quantization error is going to be uncorrelated with the input in the sense that their correlation coefficient is 0. Zero correlation. That's what we mean uncorrelated. Okay. And the third is more than error is white. Error is white. So that needs some further elaboration. What do we mean error is white? So basically, we are when when we say the error is white, by definition, that means the cross correlation or autocorrelation. So if you think of E of I and E of J, okay, two different samples. So maybe allow me to simplify my notation as EI, EJ, using a subscript, 用下标来写 to save some space. So when you consider the error of sample I versus the error in sample J, so by white, we mean that the correlation of EI, EJ is 0 if I is not J. Okay? The correlation of error between samples is going to be 0 between different samples. And of course, that is, we've already figured out, is that if I is J. That's the meaning, white, okay, in the time domain. In the time domain, if the error has this property, when we say white, we assume this property. Okay? We assume that the error, the quantization error, as a sequence of random variable, they are mutually uncorrelated. 互相是 uncorrelated. Yeah? Okay, that's a definition of when we say white. Okay? Mutual uncorrelated, mutually uncorrelated. 互相是 uncorrelated. Yeah. Or another way to say this, expected value of EI, EJ is, you can say, this value, the variance delta ij. That's another notation, delta ij. If I equals to j, this term is 1, and so on. Yeah. Is everybody familiar with this notation, delta ij? Yeah. So that's what we mean white, white. So you can convince yourself, try to ponder a bit. These three assumptions they do not imply one another. It's not like number one implies number two, or number two implies number three. There's no such thing. They need to be independently made. These assumptions we need to independently make. We need to, how do you say? We need to just separately make these three assumptions. There really are three assumptions. They really, 这真的是三个假设. They really are three assumptions. So maybe let's take a break before we continue in 10 minutes. this is 几率. The class will resume in 1 minute. Okay, so can we start? Can we restart? 可以再开始吗？Yeah. Oh, by the way, thanks for staying in the class after 加退选. Yeah, I know that you all have different options, but thanks for staying with me. All right, so let's take a look. We had 3 separate assumptions. First one, the error being stationary. Second one, error is uncorrelated with the signal. And third one, we say error is white, and I just gave you just a moment ago. I gave you that's the definition. When we say white, we basically mean that different samples are uncorrelated with 0 correlation. Yeah, assume that they're all 0 mean. Yeah, of course, you can see that. Of course, error is 0 mean. That's correct. Okay, stationary noise, error 0 mean. So if you take the cross correlation between 2 EI, EJ, they are going to be basically non-zero only if I equals to J, okay? But now we call it white. We call that now this noise, this random process is white. And white is a color by Zhaxun. So in what sense? And now I want to share with you a reason why we refer to this kind of property as white, as being white, okay? So stay with me. So now let's define cross correlation. No, autocorrelation. I'm sorry. Yeah, autocorrelation. 自己跟自己 auto correlation to itself. The autocorrelation function is defined such way, which I'll give you shortly. Autocorrelation function denoted by R. Okay, so now we are talking about the random process En. Yeah. The autocorrelation function is defined as it's an index. It's going to be indexed by M. Okay, it's a function in time, if you will. And definition goes expected value of, in this case, E. I want to say EI plus M. Okay. Okay. Let me stop here for a moment. Okay. Here assume 0 mean. 0 mean for 0 mean. Okay. Yeah. For if the error is 0 mean to begin with, then its autocorrelation function is defined as by shifting your signal. Shifting your signal by M sample and consider what's the correlation. Shifting our signal by M sample, then consider what's the correlation like that. So that's called autocorrelation function. Okay. Shift the signal by a few samples and see what's the expected value right there. And now from here, you can verify now the autocorrelation function of our approximation error as a random sequence. This autocorrelation is going to be delta divided by 12 and what? Big delta right here, denoting the quantization step. And now, delta function. Yeah, using our DSP notation. Okay, so basically the autocorrelation function is non-zero only at m equals to 0. Let me just yeah. Do you all see that? Yeah. Only if I equals to j, this non-zero with this value only when I equals to j, right? Only when I equals to j. So that's only when m equals to 0. Yeah. So now the autocorrelation function is a function in time, and it's non-zero only at time 0. So it's a delta function. It's basically an impulse. Okay? That simply follows the definition. Okay? If we define autocorrelation like that, shift the signal and consider the cross correlation, assuming that our signals are zero mean. That's an autocorrelation function, which look like a delta impulse at time 0. And yeah. So now, why do we call this property white? Why do we call it white? Because there is a property that if you take the Fourier transform of any autocorrelation function, the Fourier transform of the autocorrelation function is the power density spectrum. Okay? If you take the Fourier transform of the Fourier transform of autocorrelation gives you Fourier transform. Gives you something called power density spectrum. So that's a kind of historical reason. Okay, so you see that now. What's the Fourier transform of this function? What's the Fourier transform of a delta impulse? The result is flat, right? Right? Delta function, the Fourier transform of delta function is flat. And a flat spectrum is a white spectrum. It's just like sunlight with all the colors combined. White spectrum. So that's a notion. This is that's a reason why we call it a white signal, because the power density spectrum is going to be flat. The power density spectrum, if you take the first transform of that, the power density spectrum is going to be white. Now it becomes a function of omega, and it's going to be a constant. It's going to be a constant. It's going to be a constant of how much? It's going to be a constant of I think I want to say there's a factor of 2 pi somewhere. I think there's a factor of 2 pi delta squared divided 12, right? That's a power density, the Fourier transform of R of M. Okay, look like that. It's a flat spectrum. And just because it's flat, in between, we can say in between minus pi and pi, just because it's flat, we gave it a name, we call it white. Okay, flat spectrum is a white spectrum. Do you all get it? Do you get it, Doma? It's just a name, okay? There's a reason, give you a reason why. And this kind of my explanation, why do we call this area white if it has that property? Okay, so here in the next slide, I want you to take a look of an example, okay? So you can take a picture right here, and let's move on. But let me also mention, now, power, we are going to see a few examples, okay? We're talking about the power density spectrum of quantization noise. And in the next page, we are going to see a few examples of the Fourier transform with the autocorrelation function of your approximation error. Okay, they really can be calculated or in simulation， 用模拟的方式啊。所以 ，but I want you to pay attention that now the power density spectrum is going to be there, the factor 2 pi, but now this term is important. Delta squared divided by 12. Okay. So as you can see, delta is inversely proportional to what? To the 2 to the nth power, n being your number of bits, right? What is delta? Let's recall. Let's kind of summarize today's lecture. And here, a remark we can make that now this delta, what's delta? Delta is your Fourier scale divided by 2 to the number of bits, okay? Maybe b plus 1 to agree with the textbook notation. B plus 1 being the number of bits, okay? Mantissa plus 1. Okay, so in the next slide, we're going to see a few examples. We're going to see an example of the same full scale, but when we increase the number of bits, what will happen for the power spectrum of your quantization noise? Okay? Quantization introduces a noise which is uniformly distributed in between plus or minus half of that. And then by there, you can develop the power, you can develop the autocorrelation function, and you can take a Fourier transform finally to see its power density spectrum, to see the power, how uniformly is also going to be distributed in the frequency domain. Right? So that's what we're going to do. So now in the next slide, if you will, take a look at this next slide. Wow. So what are we looking at right here? First of all, the horizontal axis is omega, okay? Omega normalized by pi, yeah? So 1 represents the Nyquist frequency. And 1 pi represents the Nyquist frequency. Okay, the highest possible frequency right here, the full bandwidth. And you can see that now, when we increase the number of bits from 3 to 7 and 11 or 15, I should say, yeah, 4, 8, 12 or 16, b plus 1 size the number of bits. Yeah, anyway. So when we increase the number of bits from top to bottom, we see the power spectrum, the spectrum of our quantization noise. What's going on right here? First of all, when the number is slow, not slow, when the number is small, the noise spectrum is higher, and that makes perfect sense, right? And when we increase the number of bits, the noise spectrum is reduced. The power, this spectrum is reduced. It's lowered, and then when we increase the number further, it's further lowered, and when you increase it further, it's further lowered. 下降了, lowered. That making sense? Does that make sense? It's like if your full scale is going to be minus xm to plus xm in the original signal domain. Yeah. Now, when we increase the number of bits, we are going to divide the full scale into finer and finer segments. Right? 越来越细嘛，越切越细, right? When we increase 1 bit, we just making the resolution higher by the more fine-grained, 颗粒越来越小, the step size becomes lower and lower. So when we lower delta, when B increases, the quantization step size is getting smaller and smaller, resolution is going finer and finer, right? 越来越 fine, 越来越细, 越切越细. We are cutting the entire full scale finer and finer into more and more steps, more and more steps. As a result of the quantization error, of course, the error is going to be smaller, also we become smaller and smaller. That's why their spectrum looks lower and lower. Okay? Does that make sense? And also, By the way, in this simulation, this is a simulation. What do you see here? Not only does the spectrum become lowered, but also it becomes more flat, right? More flattened. 比较平有没有? More level, more flattened. B15 is really flat, okay? 11 kind of flat, 7 there you see some ripples. 3 bits, it's not so white. Okay, not so white. So that's how we describe this. Okay, this spectrum is not so white. Come on, it's going up and down. It's not so white, not flat. But this spectrum is pretty white. All the error signal when you go through the Fourier transform, the energy is going to be equally distributed across all frequencies. That's the way we look at it. Okay? So this is a pretty white spectrum. Also pretty white, maybe not so white. So now we say that when we have only 3 bits, that assumption probably is not valid anymore. When you have only 3 bits to quantize your signal, then the quantization error doesn't look very white. Okay? The spectrum is not flat. The assumption is not valid anymore. Yeah. All right, so that's a few observations I am making right here. Okay? Does anybody have any more observation? Any comment you want to make? Any comment? Any comment? Is it making sense? 有没有意见? Any comment? Any comment? If no comment, let me ask you one further question. What's the distance between this line and that line? What's the distance? That's my question. Anybody want to guess or make a comment? Yeah, I want your comment. What's the distance between this line and that line? 这有隔多远? What's the difference? In dB. Note that, yeah, we haven't mentioned that now here the spectrum is in the scale, in dB scale, in log scale. Yeah. Can anybody tell me what do you think is the difference, the distance between 2 lines, between this line and that line, with 7 bits or with 11 bits of quantization? Anybody? What's the distance? Yeah. 24. 24 or 25, approximately, right? So yeah, of course you can. Yeah, can we agree? Yeah, if you take that, it's going up and down, but roughly speaking, like 50. I read a minus 53 right here, 53左右. And this, if this is minus 77 or 78, yeah, you are right. Yeah, so we can all make that kind of a quick calculation. 24 or 25. Does that make sense? And how about here, this and that? What's the distance? Also 24 or 25. Okay. So there's actually, so I want to actually, my hint is that there is a theoretic, what does it mean, prediction. What's a theoretic prediction? What's a theoretic prediction? When we say we expect the spectrum to be white, right here, with a flat density, which takes a value of 2 pi, delta squared divided by 12, and yeah. So actually, here goes a theoretic prediction. Here goes a theoretic prediction. So it will clear if I do this, if I show this to you. What's a theoretic prediction right here? So if now we have a spectrum, power spectrum between plus or minus pi, and the power, as I said, is going to, the theoretic prediction tells us it's going to be 2 pi delta square divided by 12. Okay, something like that. Let's take log, right? We can take 10 log of 2 pi delta square divided by 2. Okay? That's my hint. 10 log 10. It's going to be 10. 10 what? 10. That's 2 and 2. Okay, log 10 pi. Log 10 pi By the way, this is dB. Okay, in dB, yeah, in dB, that's the definition, right? 10 log 10 pi plus 2 log 10 delta, right? Yeah. So we further develop. 10 log 10 pi is a constant. We don't really care there. Plus now, this is important, 20 log 10 of delta. But then what is delta? We have an expression of delta in terms of the number of bits right here. Don't we have it? What is delta? Delta is 2 full scale divided by 2 to the number of bits, right? So now, full scale divided by 2 to the what? Number of bits, b plus 1. Okay, so you see where I'm going. Now we have a relation between the spectral density in terms of dP against the number of bits. There's a relation, a theoretic prediction. That's what I want to bring up. That's what I want to bring out. This is what I want to bring out. The power in dB certainly depends on the number of bits. If we follow all the assumptions, every assumption, okay? Now it leads to this relation. So let's complete this. So the constant, so I will not repeat the constant part. I will not repeat the constant part, but now 20 log 10, 2 down there, right? So there's going to be something like plus b times 20 log 10, 1 over 2. That's the result I want to bring out. What is 20 log 10 minus, what is that? So it's roughly constant minus 6b. Right? What is b? B is the number of bits. Yeah? So this is famously, 很有名的, the famous relation of 6 dB per bit. Okay? It has the famous name. It goes by, we call it the 6 dB per bit relation. Follows from here. Okay? When we, in digital signal processing, when we increase, when we can afford, 如果我们可以玩得起, if we can afford to spend more bits for every number, then the benefit, 好处, the advantage is now we decrease the power spectrum by 6 dB per bit, okay? We decrease the quantization noise power by 6 BT. We earn, 我赚到, we earn 6 dB for every extra bit we are willing to spend. For every 1 bit you want to spend for encoding your number, every 1 extra bit you earn 6 dB in terms of quantization noise. The noise spectrum is going to be lowered by 6 dB per bit. So that's why from 7 to 11 we have 4 extra bits, right? 多4个 bits. When we have 4 extra bits, we earn 24 dB space right here. And that's an advantage, give and take. Giving more bits, you reduce the quantization noise power. Okay? All right. So with that, I think that's all I want to share with you for this lecture of quantization and noise. Hopefully you feel that it begins with rounding. Rounding is very simple, right? Was so simple, but now you can see that it's a deep water right here. The concept can go very deep, and I encourage you when you go home to contemplate on what these assumptions really are. Okay? They're not that straightforward to digest. 其实没有那么直观. Some concepts are not that straightforward. That's in my opinion. 个人心得. Okay, yeah. Can we take a break of 2 minutes when I switch? Okay, so let's take a 2 minutes break when I switch to my next lecture. Yeah, and you may go, stretch and do stuff. Yeah. 好，那帮我一下，下一个啊。 Okay, so can I erase this? Yeah, can I erase this? 可以擦掉吗？啊。Okay, so also as a reminder, so tomorrow we have our first FUD, right? The first follow-up discussion session is going to be tomorrow in class. And we do the same format. First hour will be in English, and second hour will be Chinese. Okay, so in the next lecture, I give you this title, okay? We've talked about conversion from continuous time to discrete time. Now let's do the opposite. We will study how to convert from discrete or digital. Actually, now we can finally talk about digital signal processing, right? We talk so much about quantization, tools complement stuff now. So now, depending on your choice, call it digital or discrete time, but anyway, we're going to go back to the continuous time domain. How do we do that? That's the topic, D2C conversion. And you will see in a moment that really the conversion is all about interpolation, and the function we use for interpolation ideally should be the sync function. So D2C, ideal conversion as a sync interpolation. And by sync function, you will be taking a look at this function, okay? Sync function, in my course, I define it as sine theta divided by theta, yeah. Okay, the sync function, okay? I know that some other textbooks, sometimes there's a different normalization factor. In some other textbooks, sync is, let me say sync underscore. Could also, in some other textbooks, it can also be defined by sine pi theta divided by pi theta, okay? So it's not that super important. But here I stick with my notation, right? Sync function is defined in my lectures. We will consistently define it as sine divided by theta, okay? Sine theta divided by theta. So let me just erase this to avoid confusion, all right? Sync interpolation. We'll see in a moment. All right, so now a bit of a recap, okay? When we introduced C to D conversion a few weeks ago, we mentioned that in the time domain is equivalent to a multiplication of our original signal with something we call S. So a bit of a recap. What is S? Suppose that our sampling has a period of big T. Then we define an S function. Define an S function as, still in continuous time, define an S function as a periodic repeat of the delta impulse. Delta t minus t minus 1 sampling period, and they are equally spaced, and they extend infinitely toward positive time and negative time. Okay, we have defined an S function conceptually. 观念上啊, conceptually, we define the S function, and we can argue that sampling is equivalent to multiplying your signal with S, equivalently. So that's S of t is right there. So by the way, S of t, when we have, let's say, if our signal, let me draw a random signal like that. If this is our signal right there, right? If this is our signal in continuous time, and when we multiply the two of them, where is it? So when we multiply the two of them, let's say this is a result after sampling. Now I recollect. Okay, now I remember. The result after sampling is denoted by S, small s right here. The result after sampling is defined, can be thought of as equivalently as to multiply your signal with S. So that's the result of sampling, turning our continuous time signal into a sequence of impulses. And the end result is, now I'm going to use the dashed line, 用虚线. Dashed line, and the result is a sequence of impulses with their heights modulated by the signal value. The height, or the signal value, the impulse height is modulated by your signal. Okay, that's a result after sampling. Okay, this is a result after sampling. All right. So kind of fast forward, a few lectures ago, actually in the first lecture, in our very first lecture, we have argued, we have made a discussion. We discussed that when we consider the frequency domain. When we take the result of sampling to the frequency domain and denote it as a spectrum of as a spectrum, okay? As a spectrum. Now the result is gonna be the original spectrum but shifted and summed, okay? The original spectrum denoted by letter C, okay? The original spectrum. So now we are going to consider what if we take the Fourier transform of this. What will happen, okay? The result is going to be the original spectrum shifted and summed, right? The original spectrum shifted by k times basically the sampling frequency times 2 pi, okay? So let's take a look. Please try to remember that we have made this discussion that if the original spectrum looks like a triangle, just for illustration purposes, if the original signal looks like original spectrum looks like a triangle, then after sampling, the new spectrum is going to be shifted, and it will occur periodically in the frequency domain. It will occur. It becomes a periodic spectrum in the frequency domain, right? I should be careful about my choice of color. So let's say I would denote my used color, okay? Let me denote my original spectrum using green. So if this is the original spectrum, 0 elsewhere is, if we assume that the original spectrum is band limited. Do you remember that? If we assume that original spectrum is band limited, if the bandwidth is finite, then after sampling, when we have a sufficiently high sampling rate, the shifted copies will not overlap with the original spectrum. So we say the aliasing can be avoided, okay? It's no interference. Now the new spectrum, I use yellow. The new spectrum becomes the periodic one, okay? 这个是重叠, you know what I mean. The new spectrum, after sampling, now has extra copies indefinitely. Infinitely many copies, 0 right here, 0 right here, 0 right there. So this is yellow is after sampling, green is before sampling. That's what we mean. Okay, that's what we mean. So let's write it down. The Fourier transform. The Fourier transform of x. No. Let me just, yeah. The Fourier transform after sampling is going to be the original shifted and summed. Sum over all k, and where here that's the sampling equals to the 2 pi times the sampling rate. So that's what we had during the first week. Okay, during the first week, we discussed this the effect of sampling. What the effect caused by sampling. In the spectrum, the spectrum is going to be, in the frequency domain, the spectrum is going to be shifted and summed. And with it, also there is a factor which is not super important, but actually we will discuss this factor. I think we will discuss this factor tomorrow in the FUD. In case you haven't looked at the FUD questions, please do so. Tomorrow we delve into more details about this factor, but let's assume that this is correct. A constant that is not that important, but this is correct. Okay? All right. So now the idea is that, let me read it first. Assume that our sampling rate is high enough, more than 2 times bandwidth. That is, if our sampling rate is more than 2 times the bandwidth B, now then we can use a low-pass filter to retrieve the original signal from its samples. That's according to Shannon's sampling theorem, Shannon-Nyquist sampling theorem. If the signal is sampled with a higher enough rate of more than 2 times the bandwidth, then we can, in this lecture, we're going to convince ourselves that we can use a low-pass filter. We can use a low-pass filter to reconstruct the original signal from its samples. That is to say, given the samples, given these, the sequence of impulses, we can reconstruct the original signal that goes from discrete time to continuous time. So that's what we mean conversion. Conversion from discrete time back to continuous time, assuming that the sampling rate is high enough. Okay? And the reason why we use a low-pass filter is because now, to get the original signal in the time domain, so let's think about in the frequency domain, how do we retrieve the green from the yellow? 怎么样把绿色的从黄色的取出来? How do we take the green part from the yellow part? Of course, we take the middle, right? Take the middle, apply, just pick this region. Just pick this bandwidth and reject everything else. That's what we're going to do. Okay, let me repeat that. To reconstruct the green spectrum from the yellow spectrum, because we know yellow is nothing but green shifted and summed, right? So to retrieve the green from the yellow just takes a low-pass filter to keep the middle part while rejecting everything else. Keep the middle part while rejecting, 拒绝, rejecting everything else. So we are going to use an ideal low-pass filter, that is to say. Okay? So we are going to use an ideal low-pass filter to reconstruct, to retrieve the spectrum and use the inverse Fourier transform to go back to the time domain. If we can successfully retrieve only the green part, zero elsewhere and only non-zero in the middle, then we can just equivalently go back to the time domain. It gets us back the continuous time signal perfectly. That's the idea. Okay, so we will start with the frequency domain representation. And also, let me just read this. In this lecture, we will calculate the impulse response for that ideal low-pass filter. Okay, we'll do that in a moment. And then later, I will point out to you that what low-pass filtering is doing here essentially is a sort of interpolation. Interpolation in Chinese is 内插法, 内插, interpolation. Okay, so here is sort of a summary of what we are going to do next. Okay, here all I have written right so far is a summary of what we are going to do next. So let's delve into, get into more details. Now, okay, so now let me try to copy a few things. If given that the spectrum after sampling is a scaled summation of shifted copies of the original, I should add a J right here. Omega minus K times omega S, sampling frequency in radian. Given this relation, so now allow me to introduce the ideal low-pass filter, an ideal low-pass filter. Okay, so here we have a frequency response. We have a frequency response that goes H, that's denoted by H. And if we define this frequency response to be constant T when frequency is lower than, bless you. Seriously, when you go to America, every time you sneeze, people around you say, bless you. Please, anybody who's been to America? In Greece, do you do that? Yeah? Yeah. Like European people, in different languages, European people, German people, everybody do that. Every sneeze, people say, bless you, good health. Because in ancient time, you may die. So God bless you. Bless you that you will, I wish you will recover from sneezing. So let's introduce an ideal low-pass filter, which is constant when the frequency is below Nyquist. Okay, that's the way I take it. Know that, This is Nyquist, by the way. This is Nyquist. Okay, when big omega is below pi sampling frequency, that's Nyquist frequency. It's Nyquist. Basically, this is, if you think about it, it's f times 2 pi. That's what I mean. Half of sampling rate times 2 pi, because now we are using a unit of big omega. Okay, So if we define an ideal low-pass filter as if it has a pass band in between that and zero elsewhere. So let's take a plot. The ideal low-pass filter right here now is flat in between plus or minus what? Pi. I want to say, it's easier to say, this is big omega s right here divided by 2. Okay? Big omega s divided by 2. Half of the sampling rate, and omega has a unit, let's say radian per second. Okay? This is an ideal low-pass filter, having a pass band for low frequency and stop band for high frequency. And we call it a low-pass filter, an ideal one. Okay? Ideal in the sense that the gain is a constant. Ideal. And its gain is 0 outside, okay? Ideal in that sense. Constant in the passband, 0 in the stopband. Ideal, an ideal filter. Yeah. So conceptually, if we apply the ideal low-pass filter to the spectrum, to our spectrum after sampling, the spectrum after sampling look like this. This is H. And the spectrum after low-pass sampling is, the spectrum after sampling is a repeated sum of that, yeah, like that. The yellow one I was talking about, like that. And you extend indefinitely in the frequency domain. That's a result after sampling in the frequency domain, right? So imagine if we now imagine, hopefully it should be clear that when we multiply this frequency response with our spectrum right there, you get back only the middle part. Okay? That's how we read it. When we multiply this frequency response with the spectrum after sampling, we keep only the middle part. And what is the middle part? The middle part is the original spectrum. Is that clear? When we multiply, when we multiply this function, 1 over t, okay? Here, 1 over t is 1 over t, right there, okay? When we multiply, can we agree on that? Can we agree? We all agree that when you multiply by taking a look, or taking a close look, take a look. If we multiply this frequency response with this spectrum, what's the result? The result is the green part right there. Can we agree on that? The result is a green part, only the middle part. Okay, let me keep using the color green to refer to the Fourier transform of the original spectrum. Equals to h j omega times the spectrum after sampling. Okay, can we agree on that? By inspection, 用肉眼看, just by taking a look. By inspection, can we agree on that? Okay, if we define, not 1 over t, oh, sorry, it's a t. Yeah. That looks more correct. Yeah, we need to multiply t with that to cancel that. T will cancel with that, okay? 好，谢谢啊 Thank you. Okay, yeah. But the spirit right here really is to keep the middle part. Okay, to keep the middle part, it takes a low-pass filter. And what's the gain? If you take a closer look at that expression, you will realize that the gain should be t for a perfect reconstruction with the correct value. Okay? Okay? So that's the first point I'm making right here. Okay? The first one I'm making right here is that from equation, from all the definition, it should be clear that indeed, by applying a low-pass response, you can get back the original spectrum. And the gain needs to be t. Okay, the gain right here needs to be t. That's the first remark. And the second remark, let me read it for you. This action, 这个动作, this action is called filtering. To multiply a spectrum with a response, we call it filtering. Filtering refers to multiplication in the frequency domain. Frequency domain multiplication. It's what we call filtering in this course. Okay, in this course. But the third one is really important. Okay, the third point is important. We are running out of time, but next time when we meet next week, we'll go through this. But immediately, for those of you that have taken signals and systems, you know that multiplication in the frequency domain is equivalent to convolution in the time domain. Okay, so equivalently, we are going to see that when we suggest we want to apply filtering, that means we need to do convolution in the time domain. Okay, convolution what? Convolution of your xs. Convolution of xs with the inverse Fourier transform of big H, which is called the impulse response. Which is called the impulse response. Impulse response. H, small h, which is defined as the inverse Fourier transform of big H. So next week when we meet, we will calculate what's the inverse Fourier transform of big H. And we call it an impulse response, which we will be convolving with our sequence of impulses, a sequence of delta functions, the sequence of spikes, so to speak. And with that, I'm running out of time, so thank you for being here. We'll see each other tomorrow.好，谢谢。